So there we go. I will move to this computer. You will see where we have a fancy camera set up here with the camera there and the camera here. That's just to show you that we are actually inside the Dwingeloo radio telescope. What you see here on the title slide is a view also from the inside of the Dwingeloo radio telescope, also with two gentlemen in there. That is not us. This is a picture from 1950 something. The Dwingeloo telescope was built in 1956. But it's actually the same cabin that we are in.
I get a comment that the audio is low. Is there a way maybe we can...
In the Zoom, maybe we can put it on. Is it low for...
Let me see if we can increase it.
Audio settings down.
Yeah, the audio is a bit low.
Okay, let me see if we can increase it. No, this... Oh yeah, this is...
That's at
is
the
it
max.
better now?
Did that help? We try to increase it a little bit.
Yeah, it's still a little bit low.
Okay.
Let me see if I can increase it here. Sound. No, it's already at the maximum. And then we might have to put it closer to...
Oh.
Hang on.
Oh, sorry,
Yeah.
I've touched the microphone. Did this help? Does this help a little bit?
Yeah, that's the solution. You need the mic a bit closer.
Yeah, it's 1 over r squared, right? Yeah.
Okay, very good. Thank you.
Absolutely.
So this is a view. You now have two views of the inside of the radio telescope, one from the 1950s, one from the one from today now. If I move to the next slide, well, this was the highlight of this week. I thought I'd include it. I think you have seen this from the UK as well, right? This was the aurora of last Monday. I cycled to the telescope to take this picture. It was quite cold, but well worth the effort to cycle here. That has nothing to do with the talk other than that here's a pretty picture of the radio telescope. Here's another pretty picture of the telescope, which shows it being hoisted up in 1954. What I like about this picture is that it really shows that it's a very old dish, well, 1954. Here is another view. This was 1956 in April. It was the opening of the radio telescope. There's a little Majesty the Queen for scale here. The dish has a diameter of 25 meters. This radio telescope was the largest in the world in 1956 until the Jodrell Bank telescope opened in 1957-ish. So it held the record for a couple of months. Another photo for scale and to show the environment a little bit. We're in a national reserve, nature reserve. There's the heath, which looks like grass here. We're situated next to the building of Astron, which is also where Joe Kellingham is working. I work there in my spare time as well, whenever I'm not in the radio telescope or at home for that matter. That's the professional Astron headquarters where they operate the Westerbork dish and the LOFAR, the Westerbork dishes and the LOFAR radio telescope. But this is the historic Dwingeloo radio telescope, which is operated by the Camras Foundation, which is a crew of volunteers running this dish, doing some maintenance and installing fancy new electronics to make it work. In fact, it works better than before, because in the 1950s they did not have a computer for doing data reduction, and that helps quite a bit. Not a pretty picture. We like this regional kind of sheep here. The Drents heideschaap, for those who know it. And then we're back to the beginning with the picture of the two people in the telescope. And that is where I will begin a story of, there I will begin just observing. What I should have mentioned before, if you have questions, please feel free to interrupt us. It helps really a lot to answer the questions while they appear rather than afterwards, when we can also have a questions session, of course.
And you can either speak up or type them in the chat. One of us will be monitoring the chat as well.
Okay, there we go. You may know the tool on the right. the tool is called Stellarium. It's an open source free observing system. You see a lot of stars there. This is not, well, you see the Big Dipper, looks like the Big Dipper, which is called not the Big Dipper. It has a different name in English. Okay. Here's Polaris. What we have done, we have integrated the steering of the radio telescope with Stellarium so that you can see where the telescope is pointing at the moment. And you see that at the moment the telescope is pointing in northwest direction. You actually see a hint of the Astron building there. In northwest direction, telescope as altitude is plus 43 degrees. The elevation is 43 degrees. And as it happens, we're pointing inside the galactic plane. You see the Milky Way there. Now there's another tool which shows you where in the Milky Way we are pointing. So the fact that we are pointing in the Milky Way, you see here, because we see the Milky Way and we see the telescope pointing in there. But here you see as well in this line that reflects that the blue line is the pointing of the telescope, the straight line is the pointing of the galactic plane. But here you see our galactic longitude. We're currently pointing inside the galactic plane, pointing at galactic longitude 105 degrees. Well, you can guess what kind of demonstration I can give now. What would we want to see in the galactic plane? Maybe it helps that there's a tool called H1 demo. So I can just fire up the radio and see what kind of lines we can see. Let's see. So we are starting the backend computer now. That's starting up. It's an USRP. I think it's getting something like 6 megahertz now. And we are seeing one of those 2 megahertz of this. And here you see the hydrogen line. It's with a 25-meter dish, the hydrogen line is quite easily visible. At the moment we are integrating this signal for 10 seconds. We can also choose not to integrate it or integrate it at 0.2 seconds or so. Then you see that the live signal looks something like this. Of course it looks much more pretty if you, let's keep that signal and integrate a bit longer, and you see the noise disappear and the signal being there. As you all know, is that we see the neutral hydrogen line, and we see also Doppler shifts of that same hydrogen.
Slightly bigger.
Yeah. So there's the hydrogen line again. You see the neutral hydrogen line and Doppler shifts of it. So we know that this is local hydrogen and this is hydrogen with a velocity. Well, the frequency is higher, so Doppler effect means it's coming towards us with a certain velocity. We have done the computation here, it's coming towards us with a velocity of something like 50 kilometers per second. We have corrected for the local standard of rest here already. If we would not have done that, by the way, oh, well, it doesn't matter a lot at the moment. So these Doppler shifted versions of the hydrogen line, they come from several spiral arms of the galaxy. On the left you see our pointing in galactic coordinates, so we're looking into this direction. See if I can make that bigger as well. Still in the view here, yeah. So the top view of the Milky Way that we see on the left is of course not a photo of the Milky Way, because we cannot fly out of this 100,000 light years galactic disk, take a photo and send it back home. It's a model. The underlying model looks something like this. So it's a couple of spiral arms, the brightest of which is the Perseus arm. We live in the Orion spur, and there's this outer arm which is painted in red here. Now, you can, if you do a lot of simplifying assumptions, you can convert these spiral arms to a velocity and then to a frequency at which we would expect these spiral arms. These arms I can highlight on the right as well. And there you show that there you see that either the measurement is wrong or the model is wrong. Well, the measurement we're doing right now and we've done it ourselves, so that is correct. The model does not 100% agree with our measurement currently, but I dare say that this very bright peak here is the Perseus arm, and this thing here, this feature here, would be the outer arm. We could verify that, for example, by, well, we can actually change the coordinates, or galactic coordinates. What we could do is move the telescope a little bit and see if the spiral arm structure that we measure changes as well. So what I will do is keep a hold on this graph that we have just measured. We've integrated for 40 seconds, which is a pity. I could have integrated longer. And I can send the telescope to different galactic coordinates. Let's go a bit, I think this is a bit higher in altitude. Let's go to 120 degrees. We are not now at 105, so this will be a 15 degree slew. Let's send that set point to the steering computer, to the console computer. And it will do what I expect. Yes, we will go up a little bit. Now, because we are moving, I will put the integration to a lower value, because integrating while moving is not good practice. So because I stop integrating, the noise goes up, but you see also the spiral arm structure change slightly. This peak gets brighter, this peak gets lower, but also the position shifts a little bit. This is actually how you make a model of the Milky Way. By measuring those peaks, I can actually do that. Measure the brightest peaks and show on the left to which points in the galactic plane they correspond, with the same simplifying assumptions for the rotation curve of the Milky Way. You see that also doesn't quite work, but you see those lines being painted there. That's actually a model that we are deriving from our live measurements that we're doing now.
I have a question here in the meantime.
Yeah.
From Andrew, does the model on the left show the optically bright arms of the Milky Way or optically dark lines? The reason I ask is that I understand hydrogen line from optically dark areas.
Well,
I think the lines show here are the optically bright ones, and that's also where the hydrogen is coming from. For us, seen from the Earth, it looks dark, but that's the dust we see.
And how I understand it is that the dust is between the bright arms, but so yeah.
But okay, but the hydrogen emission is coming from the bright arms.
Yes.
Right?
Yeah.
Okay.
Yeah.
Wait. Yeah.
So the telescope. Well, you see that the spiral arm structure changed. Let me remove the lines and the peaks so that you really see that we have two totally different profiles, but just moving the telescope a couple of degrees, 15 degrees. So if we would do this for all galactic pointings, for all galactic longitudes, we could draw a model of the Milky Way. And we have done that a couple of times, of course. And it never really matches the model on the left. Which means, yeah, the model on the left is also actually a bit outdated, I've been told. Is there another question?
No.
Oh, okay, cool. Then there is another thing I would like to show, and that's just measuring noise. We are now pointed at, over here. Oh, that's in the constellation of Cassiopeia. And there's a very bright radio source in that constellation. That's Cassiopeia A. Thomas can move there. Now I disabled the hydrogen view, right? We'll start it again. Yep.
Offset, and we go to Cassiopeia.
There's the hydrogen line again. I will hold this, stop integrating, because we're moving. We are moving the telescope 7 degrees down now.
We'll put it next to.
Yeah, so Cassiopeia A. Let's see where it is. This is so nice to have a sky where you can do Control F. I've done some optical sky watching sometimes and can never find stars. I missed the Control F there. Cassiopeia A, if you zoom in Stellarium, you see that there is a supernova remnant there. So there was a star which exploded, and you see the very nicely circular shell that it produced. You also see that we are mispointing because the telescope stops a couple of degrees to the right of Cassiopeia A. That is intentional. What I would like to show is the amount of noise that we now receive from the telescope. Let's see. Also, I forgot to open this tool, which also shows that we are to the wrong that we didn't do our pointing well, because we show that the telescope, which is the blue one, is not pointed at the red one, which is Cassiopeia A. A continuum demonstration will show you the amount of noise that we receive from the telescope. Let's close that one, and we see that this is the amount of noise that we now receive. We are pointed 2 degrees to the right of Cassiopeia A.
Yeah.
Yeah, so 1 second, I will rearrange a little bit. So there you see that telescope is to the right of Cas A. The red dot indicates the amount of noise we receive now, and when we move the telescope towards Cassiopeia A, what we expect is that the noise will increase. The telescope is now moving to the left. Because this is a structure of 140 tons of steel, it takes a little bit before it starts moving. It will accelerate very, very slowly. I was telling that it would go up and it goes down. That might be something like a side lobe of the beam, or it's just noise. But as we move closer, we expect the main beam of the telescope to be about ½ a degree. And actually we move closer to Cassiopeia A, and indeed the noise, the intensity increases a lot. If you could go to -5 degrees or something.
Yeah, it's already,
Yeah,
it's already
okay.
on.
Yeah.
-5?
Yeah. This tool is up for an update because it doesn't show the numbers on the right, on the left, or on the y-axis. I think it will if we move far away from it. But you see, actually, this is how you make a scan of a bright source, and you see that the amount of noise increases. Now, what is also very nice, a nice thing you can do, is do this measurement of the total noise, which is not a line. This is just the noise, the signal on all the frequencies. We can do the same thing. There we have the dB scale. Yeah. Yes. Sorry, Thomas. What we can do is plot this noise in the same graph that we did previously in the hydrogen line viewer. That we have here. It's still measuring. We have 2 radios, in fact, so we can use them simultaneously. So there we go. We are now pointed. Let's integrate a little bit here. Oh, maybe we should go to -1. Would be nice. Could you go to -1 degree of Cassiopeia A?
Yep.
So then we're going to the left again. I like doing this with the telescope, moving it a lot. I actually wanted to be a train driver, but if you move a lot, that's really not how radio astronomy is supposed to work. You're supposed to integrate somewhere there for hours and hours, but just moving around a lot is what I like to do.
The part you're missing online is the sound of the telescope that is moving, but we will walk to the engine later on with sound, so you get a feeling of it as well.
Okay, this is a nice place to stop the telescope. I think we are doing that because the noise is not increasing yet. I will do a reference measurement here. Integrate for a little bit. Well, that'll do. I will hold the signal here. The hydrogen signal is now what we're most interested in. We know what this graph will do. We will hold the hydrogen signal here. We see 2 spiral arms to the galaxy, which are, well, it's the Perseus arm again, and the local hydrogen. When we now move towards Cassiopeia A, what we expect to see, and I think we're already moving, no, almost.
No. We should move, yeah?
Yeah, if you could,
I was
yes,
waiting for
please.
you, sorry. Yes.
Yeah. You already see when we start moving, you see the total intensity, so the baseline of all the signal will go up. And that's what we expect. All the frequencies, the signal on all frequencies will increase. And that really only happens when Cassiopeia A, the real supernova remnant, is inside the main beam of the telescope. Now we are integrating for 30 seconds. I should not have done that. Well, we'll integrate a bit shorter. What you see now is that the total intensity has increased. Now I can start integrating again because now the telescope is standing still. The total intensity has increased by, oh, that's surprisingly actually the same amount of decibels. But you see also that there are dips in the hydrogen signal. To see these kinds of, that is hydrogen in absorption. So the bright emission on all frequencies is absorbed by hydrogen atoms between us and Cassiopeia A. And these hydrogen atoms absorb some energy from the continuum emission, and they decide, hey, I will go into the wrong spin direction. I can use that energy to go into the wrong spin direction. And that's why we don't see hydrogen at this frequency, but also not hydrogen here. Those are hydrogen atoms that absorb this signal and have a velocity relative towards us. And now there's all kind of fancy things you can think about. They are hard to reason about, but for example, why are these features narrower than these features? I think the reason is, and Thomas will correct me if I'm wrong, but that the hydrogen that we are receiving here is from the entire beam of the telescope, which is ½ a degree. But this absorption can only be in the line of sight from us to Cassiopeia A, which is a very, very narrow beam, because it's the light coming from Cassiopeia A, which is a point on the sky, basically. As you can see, if I zoom in, you can the orange circle is representative of the size of the beam of the telescope, and Cas A is really a lot smaller. See? And actually, now that I look at it, these two radii may correspond a little bit to the relative sizes of these two circles may correspond a little bit to relative widths of these features. I'm bluffing here.
Maybe you can enable the model. Does that show anything interesting?
It does. A little bit. Well, yes, it shows you the Perseus arm in emission. So it shows you that these features are, they do correspond to the Perseus arm, which is not too surprising because in galactic coordinates Cassiopeia A, well, it's over here. So yeah, we do see the Perseus arm here.
I have a question in the meantime. If there's a live video of the dish, there's not. And even if we had it, it's dark now outside and there's really no light over here, so you wouldn't see anything. Of course, it would be nice to have a camera, but for RFI reasons, there is not a camera here in the neighborhood.
We're thinking about doing the same as NASA has, that to have a rendered model of the pointing of the telescope on the website, which changes daytime and nighttime. There's so many projects to do here. So this was Cassiopeia A. Oh, I have a list of objects we wanted to see, and I hid the list. There it is.
I think we were going to the high velocity cloud, correct?
Yes,
okay.
And that's actually nearby. Well, in
wait 1 second.
Yes. Yeah.
Andrew asked, does the double dips close together occur because of the line of sight goes through an arm at 2 points on the left?
Yeah, that's right. So the feature is the Perseus arm. We see it in emission and in absorption. It may be that this is just a broad absorption dip with a narrow peak going towards it, going through it. That's just me interpreting it at the spot.
I don't know exactly.
That's also
it's a good question.
Maybe I can add a bit to that.
Sure, go ahead.
Actually, the arm is split up in two. What you see is that the arm is actually it has two features, which is a slight splitting of this arm. which is not seen in emission because it's too broad, and it becomes apparent in the absorption lines because of the narrow beam and consequently narrow or higher spectral resolution that you get.
That's very nice. Thank you. I learned something today. And that is why we do hydrogen in absorption. Or we would have needed a bigger dish. I think maybe the Effelsberg telescope would have resolved the two. Is that correct, Wolfgang?
Possibly yes, because they have a narrow beam.
Yeah.
What you can actually do if you want to do that eventually, you could look at OH and the absorption of OH, and then it becomes even narrower because it's a heavier molecule, and then you will see that it splits up even further.
We have actually done that, just like you did, but we're not going to do it live today. I have another very good question. How much of the signal is lost via the link to the computer? So actually we have a low noise amplifier in the focus point of the dish. So any signal that is picked up by the antenna is amplified, and then it's going on a cable of 50 meters down to the computer room here. So the loss on the cable is not a problem because it's already amplified. So we don't have a loss because of that. Let's move to the high velocity cloud.
Yeah. Oh, wrong button. Oh, terribly wrong button. There we go. Telescope is moving. We're moving towards a high velocity cloud, which is at galactic coordinates 131.1. Which is apparently even higher up. It's 18 degrees in elevation going up. So you see that the dish is gearing up now, and it's moving quite fast actually. And I should of course show the live measurements, not those. I can disable this one. Stop integrating because we're moving. We're still moving through the galactic plane. The high velocity cloud that we're moving towards is at 1 degree galactic latitude only, so almost in the plane.
So a bit of background on what we're going to see now is that, so the hydrogen we have been looking at so far is the hydrogen in the arms of the Milky Way, which has very predictable speeds because of the spiral structure of the galaxy. We're now going to look at smaller clouds of neutral hydrogen that are close to the Milky Way. And they're actually falling back to the Milky Way. They're approaching the Milky Way, so they have a negative velocity from our perspective. And the velocities we see within the Milky Way, as you see right now, so the three arms are, let's say, between -100 and 100. But these high velocity clouds have even higher speeds. And we should actually have parked next to it, but now we're on it, that's fine. So integrate a little bit. And what you see is that another small peak is occurring at -200. So it's at the right of the plot. Tammo will point at it. Yeah, over there. It's a small peak that is showing up. And this is a small, or actually it is a hydrogen cloud in the plane of the Milky Way, but it's outside of the Milky Way and it's approaching us. There are various theories on exactly what this is, but this specific one, so the small bump you see there on the right, is actually discovered with the Dwingeloo telescope in 1971. So in this room that we're sitting was this cloud actually discovered by somebody called Aad Hulsbos. And this cloud is now called Complex H, where the H stands for Hulsbos, is his last name. And he was actually here a few months ago with his family, so we could show him his own discovery to his family live on the telescope. I think it would be nice to actually hold it and move away a little bit. Then we can see.
Latitude or longitude?
It shouldn't matter, right?
Okay, longitude it is.
Actually, it does matter, but it's fine.
So I will stop integrating because we're moving. I should automate this. I have automated this.
one of the things, if you see a small bump like that, it's either something interesting or it's something interfering with your telescope. So what we do is we move a little bit just to see that the bump goes away. So it was really located at that position. And there we see, we just move a little bit. We're only, let's see,
1 degree.
1 degree off now.
No, because telescope.
And then we integrate a little bit, and you see that the very specific peak is gone. There's a little bit left of it. It's the cloud, of course, has a certain size as well.
I can be adventurous and zoom in, and then we see all the nastiness. But
yep. Oh, that's good. Yep.
Yeah.
So far, the hydrogen, so the spiral arms of the Milky Way in hydrogen is something you can see from your backyard with a 1 meter dish, or even with a can. With a small antenna, you can actually receive this. The high velocity clouds, obviously not, and all the other stuff we're going to show also not. So therefore, you really need the big dish. Of course, the absorption on Cassiopeia A is also not doable with a small dish. There's a very timely question. Can we do pulsars?
oh, that's exactly. I can show you my notes. The
it's the-
pulsar is the next thing.
It's the next one on the list. So we are going to move to the pulsar now.
Yeah, Thomas says the pulsar. There are many more pulsars than one, but there's only one pulsar we can see very nicely with this telescope, which is bright enough to see individual pulses. The pulsar is, by the way, also in the galactic plane, so we can leave the hydrogen viewer open, see what happens there. Actually, I'm going to do one more experiment with this peak hold because it's a relatively new feature. Let's see if it works a little bit here. We're moving for 20 degrees in azimuth and 10 degrees in elevation now.
I think we have discovered a new arm of the Milky Way.
Yeah, it's out there. Yeah. I do think that the conversions were correct. And sometimes it looks nice, but in some parts of the Milky Way, this really doesn't work very nicely.
So for those in the meantime not familiar with pulsars, we will be pointing at a collapsed star, which did not have enough mass to become a black hole. So it collapsed into what is called a neutron star, something of the size of a city, but with the mass of a complete sun. That is rotating very fast. So basically it kept the momentum of the collapsing sun, but now in a very small volume, so it speeds up. So we will see the remains of a star that is rotating very fast with a magnetic field that is sending radio waves. And we have a really nice demo here to actually show you what happens.
Okay.
Now let's see if we can make this work. Bear with us for a moment, and there we go.
So now I'm over here. This is a model of the pulsar. The story is this is 20 kilometers across. It's the size of a city, 20 kilometers. It's the weight of the sun, 1 solar mass, a bit more. If you take 1 teaspoon of this pulsar, it weighs as much as the Mount Everest. No light coming from it because the nuclear fusion has run out, but there's a very strong magnetic field. And radio waves can escape from the magnetic north and south pole. Let's visualize the radio waves with the light. It's the wrong wavelength, but this we can see. And now, because the thing collapsed, it started to speed up a lot. That's conservation of angular momentum, the same thing that you see when ice skaters pull their arms closer when they do a pirouette. The amount of speed up is proportional to the amount of shrinking. This thing shrank from, say, 2 million kilometers, twice the size of the sun, to 20 kilometers, imploded by a factor 100,000. So speed increases by a factor 100,000. Maybe it started rotating at once a month like the sun, but then it collapsed and the rotation speed increased also by a factor 100,000. So you see the star rotating, and you see the beams of light going around basically like a lighthouse. And if we point a dish at that, like this telescope radio, every rotation you see the noise in the telescope increases a little bit because this lighthouse, this beam of the pulsar hits the dish. So the pulsar we are now pointing at is BO329 plus 54. That's the brightest pulsar on the northern hemisphere. Where is it? Oh, it's there, but we cannot see it because there's no light coming from it, so it's not even in stellarium. But we can start a pulsar demonstration. Start another radio. So there's also hydrogen coming from this direction. But now we need to move to the time domain. And that's what this demonstration does. Now you can actually hear pulses of the pulsar. I hope you can hear them.
Yeah, I see people nodding.
Yay. So this is live pulses from pulsar BO329 plus 54. Sometimes it's a little bit silent. That's not because it stopped rotating, but because in the analogy, the light, the emission mechanism isn't very continuous. So it's like a flickering light or a light slowly changing amplitude. So the top view of this graph shows live signal coming in from the right. We know that the period of this pulsar is 0.71452 bluff seconds. The computer knows it exactly, so we have cut the signal on the top into pieces of exactly one period, and those periods we are stacking in the middle plot, so every new pulse is coming in from the bottom. And because all those, the peak happens at exactly the same spot every time, you can integrate or add up, take the average of all these pulses, and then you see on the bottom the integrated graph, which has a lot less noise because the noise cancels out if you average it. But there you also see that there's not just one peak. Sometimes you see it also in this graph. There's sometimes a little peak after the main pulse, and sometimes there's a little peak before the main pulse. And if you average these pulses, and that's a characteristic of pulsars, you get a very stable graph. And this pulse profile is characteristic for pulsar BO329 plus 54. There are pulsar astronomers that you can show this graph to, and they say, yeah, I know that one, that's BO329, but there are also, they know the profiles of the famous pulsars. Over here, by the way, you see some RFI, which radio frequency interference, which we haven't managed to filter out. So we are doing quite a lot of data processing to show this live. We are removing RFI, most of the RFI, most of the. If we would not filter the RFI, we would hear an electric fence, which sounds remarkably similar to a pulsar because it's periodic. And also what we are doing, we are integrating 20 megahertz of bandwidth, so from 400 to 420 megahertz. That's maybe a little bit surprising because we are also looking at the hydrogen line, but that's because we have two feeds in the focus. We have a feed for hydrogen and 4 dipoles around it for this 400 to 420 megahertz band. And for those 20 megahertz that we are recording, we are stacking all together. And only then can you hear the pulsar.
Maybe nice to mention how long they have been traveling, the pulses.
Ah, yes. This pulsar is at a distance of 5,000 light years, which would put it, oh, I actually drew a little dot there. On this scale is at the cursor. So the center is, of course, sorry, this here is the sun, and that in the Orion spur is the pulsar. So it's in front of the Perseus arm. For reference to scale, I don't know if it helps, but the most stars that you see at night are tens to hundreds of light years away from us. So this is still quite a far star, although on this scale it looks nearby. The scale is a strange thing in astronomy. So we have now been talking for a while, and that's what I always do when we observe the pulsar. because actually I want to take 5-minute recordings. Every 5-minute recording goes into a data point that we use for pulsar timing. If you have integrated enough pulses, you get a very clean profile, and this very clean profile you can match against, you can match it against a reference profile, and then you can see, well, this time the pulsar arrived at 0.19 seconds relative to when I started the radio. And if you measure that very accurately, and you have a very stable clock, which we do in Dwingeloo, you can combine all the timings over a year, for example, and then you can do pulsar timing, make a nice timing model, get the very accurate pulse period, but also the pulse period derivative, or you can fit the location of the pulsar. So maybe we can do that. That's not this one. Yeah, so if we integrate it for 310 seconds, that's 5 minutes. So I press exit here. When I do that, a pipeline will start running, which will remove more radio frequency interference. That's easier if you have the whole measurement done. You see here that it threw away a couple of bands. That's a pity. Also, you see here the 20 megahertz of bandwidth from 0 to 420 megahertz. You see the pulse, the main pulse here. You see a pre-pulse, the pre-pulse and the after pulse also as well. You see some channels are brighter than other channels. We have divided the band into 200 or 300 channels here. Some are brighter than others. What we see here is actually scintillation. So constructive or destructive interference of the radio waves taking a different path to a cloud through a bunch of electrons. This is the same thing that makes stars twinkle when you look at them, except what makes stars twinkle is the scintillation of the atmosphere, Earth atmosphere, and what we see here is the scintillation due to the interstellar medium, the stuff between stars, interstellar medium. There's not a lot of stuff between stars, but if you have 5,000 light years of not a lot, it's still a lot of electrons, and those cause this scintillation. If you monitor this scintillation for a while, you are actually monitoring the interstellar medium by watching this pulsar. Also, a feature that's more obvious in this plot is that the top frequencies arrive earlier than the lower frequencies. That's dispersion. The amount of dispersion is also related to the amount of electrons that are between us and the pulsar. That's actually one of the ways to measure how far the pulsar is.
We have a question in the meantime from Herman about if we see RFI at 1420. So not specifically at 1420. Apart from HDMI cables from the Astron building next door, that's actually the biggest source of noise at 1420. But you already noticed the pulsar is indeed at 400 megahertz, and there is a lot of RFI. But actually, for us it's RFI. Of course, those are primary users of the band. So it's just other users of the band. Let's put it that way.
The RFI sorry. I want to do one thing. If you sorry, this is the integrated pulse of these 5 minutes, and I can just show you the pulsar timing now that Herman is here.
Sure.
This shows the latest measurement in Tammo, or Tammo 2. There you see that the model doesn't quite fit. So this is the measurement we just took against a model of the pulsar. This is where the model says that the pulsar should arrive, and this is where the model says it should arrive, and this is where it does arrive. So the model is wrong, but we can fit a new model to the data. For example, by fitting a new period derivative, well, just 2 parameters should work. And if I fit that, there's still a residual. Let's fit one more parameter, the right ascension maybe. Well, no, let's just fit a second derivative as well. And then we have a nice stable model that corresponds very well to the measurement. In particular, the last measurement, well, it's an outlier. That could also tell it that it's in a different mode. Well, to be looked into. This is actually the talk I gave in the UCARA. Let's quit that one and move on to a next demonstration.
Yeah, so we have, I think, two things left for now. We can do the OH maser, which is close by here. So I suggest we start with that one, and then we move to the very far quasar after that.
And I forgot which OH maser it is, and maybe we can switch places in.
Yep. I can find it. So let me first start the telescope moving and then talk. We have animal sickness. That's, oh, is it that low?
Oh, in the west. Oh, it is it. Yeah. Altitude 15 degrees. That should work with the 25-meter dish.
Mm-hmm.
Yeah, there we go. Yeah.
Okay, so we have been looking at hydrogen so far. So the neutral hydrogen atoms that emit some radio waves at 1420 megahertz. There are other molecules actually in the Milky Way that we can show, and the one we're going to look at right now is OH, hydroxyl, which emits in this case at 1612 megahertz. And this is a special case. I think you had a slide about it. You know how to open that one.
That. It did know. There we go.
Okay. Yeah, there we go. This is a measurement we've done earlier. Unfortunately, this one is not above the horizon right now, but we're going to move to a star, and in this case a red giant, which is a star which is not that much heavier than the Sun, but it's 1,000 times larger. And we have a nice animation of that, or a slide about that as well. It's a red giant, so it emits at a lower wavelength visually than our Sun. And this radiation is exciting a gas envelope around the star. So it's gas around the star. And that has a maser function. So it starts emitting radio waves at 1612 megahertz in this case. Because the gas is expanding and because of the maser, on how the maser works, we only see the radiation that is towards us and from us. So which is in our line of sight, either towards us or from us away. And those two peaks are very steep, and those are the peaks we're going to see. I think you have the slides here about the Sun, right? You have made them. Maybe you can quickly.
Okay, well, made them is a big word.
Okay, you stole them.
I stole them, borrowed them. So here, this is just about the size of animal signi, because it's one of the biggest objects known, even though it's about the mass of the Sun. So this is the Sun and the planets to scale. The distance is luckily not to scale, but the Sun is about 100 diameters. The Sun is about 1 million kilometers. Am I saying that correctly? Yes.
1 million.
So if we compare the Sun to some other stars, Sirius, Pollux, Arcturus is larger, but then if we zoom out a little bit, Arcturus, if we compare Arcturus then to Arcturus is here. If we compare it to Rigel, Aldebaran, Betelgeuse, Antares is a lot larger. Then if we zoom out again, compare Antares to the Pistol star, compare that to that, to that, to that, to that, to that, and then we have animal signa. So this is just a way to visualize the number 1,000 or 1,300 solar radii. One more is, this is zoomed in on the boundary of animal signi, and this is the Sun as 1 pixel. So, and just a way to say this thing is really large. We put this slide in because we knew we were moving for 2 minutes.
Okay. Have you already answered Andrew's question?
I have not answered,
okay,
so yeah. Do you want to?
No, go ahead, because we're still waiting.
Yeah, the question of Andrew is, how close to the horizon can you observe? That depends on how bright the signal is. If there's a satellite, which we also sometimes observe, we can go to half a degree or sometimes even 0 degrees and we still hear it. For sensitive measurements, 10 degrees, 15 degrees. Also depends a little bit in which direction in azimuth we are looking. You should compare to the beam size of the telescope, which is half a degree. We don't want ground noise coming in from the side lobes of the beam.
In the meantime, we have arrived at NML Cygnus, and now we start integrating, and we immediately already see the peak. Zoom in a little bit more. So we just do a long integration here so we get the noise out. We see the peak here on the right, which has a negative speed, and we see, so it's towards us, and there's a peak here on the right which has a positive speed, which is away from us. In this case, apparently, the middle is right at the OH line, so this star has no real high speed towards us or from us. So we nicely see a peak with a positive speed and a peak with a negative speed. So slowly you start seeing the other peak as well. It's a relatively small. There are nicer examples, but this one is actually clear.
Double click that.
Oh yeah, we can set it to
Integrate more.
So we keep integrating just to show the two peaks here.
You can see that we have tried to correct for the bandpass of the telescope at this scale, which is we're really zoomed into the bandpass. We could have done a slightly better job at correcting the bandpass, but you still see the features.
And we clearly see both of these peaks now. Of course, we're not going to integrate for 1,000 seconds. That would be a bit boring. I think you got the picture already. So the last thing we can do, given that it's almost an hour now, is that we move to a very distant quasar to see if we can detect it, which also is a bit of a slew with the telescope. So in the meantime, we can maybe show you the engine when it's running, because the thing you're missing here is all the sounds and the movement. So I will stop this one. You can also see very nicely the blue here is what we have moved during this talk. And you see that we have been moving inside the Milky Way all the time. So this line here you see is the Milky Way. Right now we're going to move to 3C295, which is a very distant quasar. So we're in a very radio loud galaxy nucleus that is around 5 billion light years away, I thought. And in the meantime, this will take a big slew of the telescope. We will show you the engine room.
Oh, okay. Also, we have a cable wrap, so it will take even longer. We're going to move for minus 287 degrees, which will take 5 minutes. Thank you, Andrew.
So.
Oh. User asks us, cooled feed, is it worth it? No. It would be nice, but it's really really expensive to keep cooled feed cool.
Kun je hem vast op? Can you put it on a few degrees next to it, then we have a better start. Oh, you have already.
One step ahead.
Okay. Okay, so now I switch on this camera. So one thing you have not seen yet is, so this is the screen you have been looking at all the time. That's the one we have on the Zoom. This screen is actually the control of the engine. So this is the steering of the dish.
Nicely.
And you see the part we still need to move. The red part is what we have to move. So we roughly had 90 degrees to move to the right, but the telescope decided to move 270 to the left to prevent that we wrap the cable, which we're now going to see. Cool. Well, we're not going to see it wrap, but yeah. Well, can you explain over there?
Yeah. Yeah, you can actually talk them through it, right? Oh, I will point and. Yep. Okay. So the thing is, we're filming something which we cannot see. So let's hope this works, and we can also not hear you. This noise is very loud. We're now inside the engine room. We're finding out whether the noise cancelling microphone works. You hear the thing there in the middle, that's the cables. The cables go through the center of the telescope because obviously, well, they need to go through the center. This is the engine room. This is the actual engine. This tiny thing is pulling the whole 140 ton structure around, well, 180 to 270 degrees now. You see the gears moving here? Quite fast actually. We're going at a velocity, at the angular speed of 1 degree per second. We are at top speed now. There's a lot of oil involved. There are long stories to tell about oil, which I will not tell. But what is very nice here, the oil is being pumped onto the gears. And here there's the gearbox. The total gear ratio is 1 to 20,000, I think. But these gears here are just inside a bath of oil, which is going against this little inspection window. Also, you hear a lot of noise. The oil pump is having trouble with the cold oil. We will replace the oil in when it gets warmer. This is the part where I actually wanted to be a train driver, and that, well, this works as well. Being inside this room while the telescope is moving is not really allowed, so that's why we do it on video, right? Let's close the door. And now let's hope that you actually heard this or saw anything. So we still have 120 degrees to go. Filtering, we can tell something about. We have a couple of filters in place here. Upstairs, in the feed there's almost no filtering, because we want to be able to downstairs select which frequency we want to see. We have a band pass filter for the pulsar, actually a very nice filter which has a pass band of 403 to 430 megahertz. So it keeps out DAB band, well, there's a very bright signal somewhere at 480 megahertz, which we really want to avoid. We also have a tuned cavity filter, which has a pass band of 1320 to 1340. That's a very 1320 to 1340. That's a nice quiet band around 1 gigahertz, which doesn't really have spectral lines in it. And another passband at 1400 to 1430. So that's a cavity filter. Is filtering important? Yes, it is. There's, especially if you observe close to the horizon. Sometimes we want to observe the galactic center, which comes to 10 degrees or so in the direction where there are LTE towers transmitting at 1450 megahertz, which is awfully close to the hydrogen line. So there you really need a filter. And then Herman Wigler has a very good question. Can you tell about the aperture T, cis, AF, SEFD? I cannot. Maybe Thomas can. Can we tell something about the telescope characteristics? T, cis, the G over T is of course one ratio. Is someone laughing there? Oh, that was Herman. Yeah.
I don't have the numbers from the top of my head either. So we're almost there. We will start the same demo as we have used on Cassiopeia A, but with Cassiopeia we were looking at an object that is inside the Milky Way, so the remnants of a supernova. Now we're looking at the nucleus of a galaxy which is almost 5 billion light years away, so complete different scale. So we have actually moved it to 5 degrees away. Thanks. And now we will move towards 3C295.
Our elevation currently is plus 20 degrees, so that's a nice elevation to be at.
Of course, the peak will not be as large as Cassiopeia A.
least there is something.
Whenever we do this demo, we're really happy if it works. This is a very faint object, but oh, we're already over it.
Yeah.
Okay. This is the furthest object we can do a really quick demo without integrating or anything, just moving live over it and you will see it. This is about as far as you get with a 25-meter dish.
But the cool thing is that this is 5 billion light years away. So this signal has been traveling for a significant fraction of the age of the universe. I will move back to just strengthen this plot a little bit. In the meantime, Dan is asking, are we losing much signal data due to corruption from the V2 Starlink system? I don't think that is at our band.
No.
So that's... I know that some other telescopes are suffering a little bit, but not at these frequencies, luckily. And the question, our baseline is really flat. Well, in this plot, we are not showing the baseline. The baseline would be frequency against signal, and this is distance to the source against signal. So that is the difference there. When you saw the other demonstration with the OH measure, then we saw, yeah, we can fire up a hydrogen spectrum again. It is somewhere. There it is. There you see. Oh, wow! There's not much hydrogen here. Are we doing something? Oh, interesting. Who wrote this software?
Something went wrong here.
Yeah. On the left, you see that there's not much hydrogen to see here, and also you see that the bandpass is not really flat. We have corrected for the bandpass already.
Actually, this is apparently a piece of the sky where there is hardly any hydrogen, so we must be very close to Lockman's hole.
Yeah.
We can see how far that is. Does that? I have no idea if that's in here. Do we write it like this?
You should be able to search for Lockman, press enter. And...
No,
okay.
There's nothing here.
What kind of receiver do we use? We use an Ethos USRP B10, B210, which can go up to 56 megahertz in bandwidth. Quite useful receiver to have. It's not cheap, or it's not as cheap as, say, RTL SDR, say over 2,000 euros.
I think we've gone through the demos we wanted to show.
There's this one.
Depends on the time and the questions.
I'm curious, who is user? Does someone know? Doesn't matter, I'm happy to answer the question. Well, if I could. If we could do the methanol line, which frequency is that? It's Andy, thank you, Andy. I don't know the frequency of the methanol line. I do know that we have never measured it.
Methanol could be either around 6 gigahertz and at 10 gigahertz.
Oh, and 1.2 it says, Andy. Well, 6 gigahertz would be nice. If we built a special receiver, we might be able to pick up something. We have never tried. There's still... Oh. Okay.
It's not within the feeds we have in the dish at the moment, so it would be a special project to do such a thing.
And there's still so much to explore in the band suite that we currently have. Wolfgang? Oh, sure.
Yeah, it's about 12 gigahertz. That's what we are doing with our 10-meter dish. So probably the surface accuracy of both your and our 25 meter dish is not sufficient to do anything like 12 gigahertz.
No, 12 gigahertz is out of the question, yeah. Can we click away the bug?
There we go.
So we went through most of the objects that we wanted to show. If there are questions, that would be a good time.
Or requests.
Oh yeah, we can. We can go anywhere. I'm not going away right now, and that's it, and bye bye. There must be something, some special request here.
I have a question.
Yes.
Do you folks have a website? Are you on YouTube?
Not on YouTube. We do have a website which is camras.nl. If you Google for Dwingeloo telescope, you will find us. But the official website is Camras, C-A-M-R-A-S, where M is a 3 thing.
So I'm assuming if you have new demonstrations, they'll be on the website. We can tune in every once in a while and see new.
No, this live demonstration is the first time we're doing this, except for some experiments which we did during the COVID pandemic. So normally we are open for the public and we give tours on site. That's mostly what we do. Setting this up with a laptop and all kinds of cameras is an experiment like all the other experiments that we do. And yeah, so this is not in a production state yet.
Well, in that case, thank you. I feel lucky to see you.
Yeah, I think we're all lucky, Wendy. Yeah, I have a question. Do you have many school groups round? Because what you've shown tonight is so inspiring, and I think you could. I think children would want to become scientists, having spent an hour in your observatory.
Well, we had 2 kids today. Last week we had a group of 7-year-olds, which was inspiring for us as well. The most inspiring thing about that was that I was talking about exploding stars and neutron stars, and then the kid raised his hand and asked, "Hey, aren't stars dead people?" I told him that the exploded star was not a dead person. The inspiring goes both ways. We do have also students coming here. It could be more, and we could have a professional teaching program, but we do have lots of, at the moment we do have schools coming here, and also school kids doing their special assignment for physics at this telescope using actual telescope data. That's a few groups per year, but still those students tend to end up doing pursuing a career in radio astronomy. I know 3 examples already.
Another question.
How big is the volunteer team?
How many people are we? About 60, I think, something like that.
Something like that, yeah.
So it's it's a large group. It's also a lot of different people. So there are people who take care of the mechanics, of the oil of the telescope, of the maintenance, the IT, the computers, the SDR. So it's a team with a lot of different skills, and only together we can actually keep this monument running.
I have a very nice question. Is Jupiter interesting? Let's make it more specific. Is Jupiter interesting to observe with the Dwingeloo telescope? No. Is it interesting? Yes, it is. There's indeed this Jupiter Io interaction, but that is a feature that you see at very long wavelengths. And for that we do have outside a couple of other antennas set up. Some of the volunteers set up an antenna and actually streamed the signal through a web SDR. So you can tune into our antennas, also to the Jupiter Io antenna. Yeah, if there is activity, you should be able to hear it through that system. Ted has a nice question. Can we do a transit of the moon? Well, I don't know if the moon is up.
Yes, it is.
It is.
It's
Well,
not.
yes,
It's just 9 degrees above the horizon. I quickly checked. It's almost
that's
going
very
down
nice.
now.
Yeah, we are tracking right now. Oh, it's 230 degrees. So we need some other questions first. Yeah. Oh. Let's see. How are we funded was a good question. The Cameras Foundation is funded through gifts and donations and some admittance we ask for tours. The telescope itself is maintained by Astron, the Netherlands Institute for Radio Astronomy, the building I showed that we're next to. And we get money from the government because this is a national monument. So we get paid to just maintain the national monument. And there was, oh yeah, yeah, no. One more question was Andy, EME, yes, EME. This is one of the most active EME stations on some bands, or, well, using a 25-meter dish for EME, Earth-Moon Earth communication or moon bouncing is great. However, this was a radio astronomy talk, so we have not done the EME. If you want to, you can have another tour which Jan van Welwijk or some of the other EME people, volunteers at the radio telescope, give sometimes, and they can talk for hours and hours on EME. However, if you are interested in doing EME with the radio telescope, I have one slide handy here, which is actually the talk that Thomas gave at Bukhara, and that's this slide. This is EME, but well, this is on the boundary between radio astronomy and EME. Actually, this is making a radar map of the moon. So this is where the signal. So EME is transmitting a signal to the surface of the moon, watching back the reflection, and in fact the reflection does not come from one place, but from many places, and you can map the moon in that way. When are we open to the public? In the summer we try to be open 2 days per week, Wednesdays and Sundays. Otherwise, out of the season, we try to be open at least one day per month. And during special occasions like the National Stargazing Days, the night to celebrate darkness, and some other. Actually, 3rd of October we cannot come to England, unfortunately, because it's National Science Day in Netherlands then.
So next question is what feed frequency bands are available. So we have roughly 400 to 438. So we can do the around 400 we use for the pulsars and around 435 for satellites. And then we can do 1300 to 1700, something like that. And there we cover the hydrogen and the OH lines, as well as the EME frequency for the radio amateurs. So those are the two feeds we always have in the front end. For special projects, we can put an 8.4 gigahertz feed in there, so we can receive deep space spacecraft, where we actually managed to receive Voyager with that.
And because we are in the telescope and we're still moving towards the moon, I can just grab the feed. There is a camera somewhere. Maybe if I can just show
Okay,
it
I
here.
can do it this
Oh,
way.
yeah, sure.
That's probably the.
This is the feed we used to use for 8 gigahertz. We can actually mount it inside the L-band, the 21 centimeter feed, and you see that it's a lot smaller. And then there is upstairs. This goes up. We have an elevator that goes up 13 meters to go to the focus box. There's a low noise amplifier down converter here, and then there is 50 meters of cable going down to get the signal into the cabin, into the SDRs. What is very important is that this needs a very stable clock, because typically the measurements we do need 1 hertz accuracy, so there is a 10 megahertz reference signal going up through the cable, and then the down converter takes the exact right frequency off of the signal coming in here. But this feed we only put in for special occasions. Like there will be a special occasion somewhere in November this year when Voyager 1 reaches 1 light year, and that we of course want to observe.
And in the meantime, we have arrived at the position. So same demo again as we did on Cassiopeia A and Quasar 3C295, but now on the moon. So we're still a few degrees away, and now we will slowly move over it. As you can see in the other plot in the sky view, we've made a very nice tour of the whole environment here, moving back and forth. I see another question in the meantime, SDR at the focus? No, the SDR is here in the room where Tammo and I are. Oh, there we go.
And we went a bit too far.
So what we're seeing here is actually the thermal noise of the moon.
Typically during tours we also do this scan, but then with the sun, and then we get something like 28, nowadays 30 even, 30 dB of sun noise. And then when you go over the sun, then you see all the side lobes of the beam very nicely, about 10 dB below the noise, but on the sun you still see that. So that was the moon. Well, one way to look at the moon. What's also a very nice experiment is to look at occultations by the moon. We have done that for the Crab Nebula and for the Sagittarius A. That was very nice, yeah.
Different moon result for different moon phases. Hardly. That's remarkable, but apparently the temperature we see of the moon in radio is very stable. It varies a little, but not much with the phase. Which is a bit counterintuitive, at least to me.
Unless there's another question, I will just move somewhere.
Where are you moving to?
The crab.
Okay.
Oh, we can take bets. That's what English people like to do. Is the crab brighter or less bright than the moon? Sorry, let's not.
I have another question in the meantime.
Better, yeah.
What's the polarization of the feed? So for the L-band feed, so for hydrogen and OH masers, we have it's circular. We have LHCP only for receive. The feed on UHF, so for the pulsar, is linear, and we have both polarizations. And the reason we have only one polarization of the circular feed is that the other one is used for transmit at L-band. So that one is connected directly to a transmitter. There's no LNA on that port. So we're moving now to the Crab Nebula?
Yeah. Actually, I don't know if it's brighter or less bright than the moon.
Well, we can run the pulsar, the pulsar demo, see if we get a giant pulse.
I need to reprogram it a little bit. That's,
oh, yeah, that's okay, never mind.
Yeah. What I can show that I did this afternoon while we were moving there, we can get giant pulses from the crab. This afternoon, while I was waiting, there was a pulse with signal to noise 183. So that was a quite bright pulse of the Crab Nebula, and here's the raw data for just one pulse of the Crab pulsar. It's 20 megahertz because it was at this 400 to 420 megahertz. And when you just scroll through this time series, at some point you see whoosh, one pulse. It was crazy bright. And you see very nicely here the dispersion. Higher frequencies arrive earlier than the lower frequencies. It took me 1 hour of waiting to get this one right pulse, but still. Are we there yet?
So we're almost there in azimuth, but we still have to go up in elevation. You can see that on the sky view and on Stellarium. Yeah.
Crab Nebula is of course very nice. If you zoom in with Stellarium, you see the explosion. This is the supernova remnant that went off in the year 1054.
Any luck with FRBs? Yes, we have detected a few in the past, and also one
we're at
recent.
5 or 6 now,
Yeah.
and actually 2 weeks ago we had one. So to be clear, we do not find FRBs. We read the astronomer's telegram whenever there is an FRB. We even have a collaboration that we know it 1 day before the astronomer's telegram for if Chime detects something. Then that's the same collaboration that Wolfgang is also, or the astropilot is also involved in. And then we point it at the location where we know there is a bright repeating FRB, and we hope to catch something. And I think we have a couple of 100 hours of observing, nowhere near how long Stockard has been observing. And we have 5 detections, which is also nowhere near what Stockard has. I don't know what the count for Stockard is, or if they even keep count.
I don't know the number, but maybe 200, something like that. But these are thousands of hours of observation.
Yeah.
The fact that you don't know the number, it says already it's high.
So we're moving closer to the Crab Nebula. The baseline is already a bit lower, which may mean
Horizon.
The moon was low on the horizon. Yeah.
The Crab and the Moon are about the same in terms of Jansky, about 900 Jansky each, I guess, so as far as I recall.
It's dependent on frequency, I think, as well. Or?
Yes, I'm talking about L-band, so.
Okay, yeah. Well, Crab wins.
But it's
close.
Close, yeah, indeed.
Well, if there are no more questions, maybe we can leave it at this.
Yeah, thank you very much. Thanks from all of us. I'm sure if I've said this before, but if you were in a hall demonstrating to us, you'd have a standing ovation at this point. I think that was just remarkable, absolutely extraordinary. Just one thing I will say, and that is next year we will all have an opportunity of visiting Dwingeloo, because we've been invited, or they are hosting EUCARA 27 and have invited the community to their site. So I'm already looking forward to this, and it is well over a year away. But thanks for the invite. Thank you very much for this evening. The video will be up next week, and it just remains to say thanks again, and we'll get you back at some point. You take care now. Bye-bye.
Thank you.
Thank you. It was great to do this. And see all of you.
Wow, thank you.
Okay.
Bye-bye.
Have a good evening.